The critical role of baseline inspection in integrity management for CCUS new-build facilities, ensuring safety and reliability in carbon capture facilities, understanding CO2-driven degradation and the importance of baseline data. Executive Overview of CCUS and Integrity Management. A carbon capture, utilization, and storage (CCUS) facility is a highly engineered asset intended to manage CO2 safely from emission sources through capture, compression, transport, and injection phases. In a new build process, the early establishment of an integrity management (IM) framework is fundamental to achieving long-term reliability, safety, and environmental compliance. Baseline inspection sits at the very foundation of integrity assurance because it provides the first comprehensive understanding of the facility's actual physical state before commissioning and early operations. This foundational dataset is essential for future comparisons, risk-based inspection planning, and degradation prediction throughout the asset lifecycle. Without a proper baseline, operators face significant blind spots regarding fabrication quality, pre-service anomalies, material mismatches, or early-stage defects that would otherwise be detectable before the introduction of CO2 streams. A new-build CCUS facility typically involves novel materials, high-pressure CO2 systems, impurity-variant operational envelopes, and unique corrosion or embrittlement mechanisms. These operational characteristics require a stronger-than-usual emphasis on knowing the initial condition of pipelines, vessels, compressors, wells, injection systems, and auxiliary units. Baseline inspection therefore acts as the anchor point for future trend analysis and anomaly assessment, ensuring that operators can distinguish between newly developing defects and pre-existing conditions. As regulatory pressure and public expectations surrounding CCUS safety increase, authorities and industry standards also emphasize traceability and early asset condition documentation. Thus, this presentation aims to articulate the engineering necessity, technical rationale, and operational benefits of baseline inspection specifically tailored for new CCUS facilities. Understanding the CCUS process and new build challenges. A CCUS facility consists of multiple integrated systems including capture units, compression trains, dehydration units, transport pipelines, injection wells, and monitoring infrastructure. Each segment introduces distinct materials, operating envelopes, and degradation threats. For example, capture units may expose metallic surfaces to amines that introduce corrosion risks, while transport pipelines handle dense-phase CO2 that may contain impurities such as water, H2S, SOx, NOx, and oxygen, all of which can accelerate internal corrosion or induce localized degradation under certain temperature-pressure conditions. New build projects present unique uncertainties, as early fabrication defects or welding inconsistencies could remain hidden until operational stresses initiate crack propagation. Unlike retrofitted facilities, new-build CCUS systems lack operational history, making the baseline inspection the only reliable initial state record. These inspections include dimensional checks, non-destructive testing, NDT, coating verification, cathodic protection validation, and material certification reviews. Establishing this complete dataset ensures that operators can later differentiate between construction-related defects and those arising from CO2 exposure, thermal cycling, or mechanical fatigue. Furthermore, the baseline data supports more accurate risk assessments, enabling the development of risk-based inspection (RBI) strategies tailored specifically to CO2 operations. The coordinated understanding of facility layout, pressures, temperatures, and fluid behavior guides where baseline inspection should focus most heavily, such as compressor discharge piping, injection tree components, or low-lying sections prone to water dropout. By mapping these threats early, operators create a more resilient integrity management plan aligned with CCUS-specific hazards. Definition, scope, and engineering significance. Baseline inspection refers to the suite of surveys, tests, measurements, and documentation activities conducted before the introduction of process fluids, in this case, CO2 streams. This includes detailed records of wall thickness, weld quality, coating condition, insulation setup, and component alignments. Its purpose is to establish the official, as-installed, condition of all critical equipment. In engineering practice, this dataset forms the bedrock of integrity assessments, allowing future inspections to quantify degradation rates, detect new abnormalities, or validate that protective systems such as corrosion inhibitors, cathodic protection, or internal linings perform as intended. Baseline inspections also improve regulatory compliance by demonstrating due diligence and adherence to construction quality standards such as API 570, API 579, ASME B31.3, DNVRPF 104, and CCUS-specific frameworks emerging in several jurisdictions. For CCUS assets, baseline inspection is even more essential due to the unique corrosion behavior of CO2 when interacting with trace impurities. Additionally, baseline integrity photographs, diagrams, and NDT records become part of the asset's permanent documentation, which is crucial during handovers between EPC contractors, commissioning teams, and operating organizations. By identifying imperfections early, costly repairs during early operations can be avoided. And more importantly, the risk of early life failures is significantly reduced. In essence, baseline inspection ensures that every subsequent integrity decision, whether operational adjustments, maintenance intervals, or anomaly responses, is grounded in accurate initial condition knowledge. Position of baseline inspection within the integrity management framework. Integrity management for CCUS assets follows a lifecycle framework that includes design, construction, baseline inspection, commissioning, operations, and decommissioning. Baseline inspection acts as the transitional checkpoint between construction and operation, ensuring that all equipment meets design specifications and is free from critical manufacturing or installation defects. This stage directly influences the accuracy of risk-based inspection programs by providing the reference point necessary for identifying deterioration mechanisms. For instance, corrosion rate calculations require initial wall thickness data, while weld integrity evaluations require baseline radiographic or ultrasonic results. Without these data points, operators would rely on assumptions rather than verified conditions, leading to inaccurate risk estimations. Baseline inspections also support integrity threats identification, ITI, and the development of mitigation plans such as coating systems, internal corrosion management, and planned maintenance intervals. In CCUS applications, where CO2 purity, temperature, and pressure fluctuate based on capture technology and injection strategies, accurate baseline data helps predict how these variations may accelerate or mitigate degradation. Ultimately, baseline inspection ensures continuity and traceability in the integrity lifecycle, enabling structured anomaly management, reliable future comparison, and consistent regulatory alignment. Applicable codes, standards, and regulatory expectations. Regulatory frameworks for CCUS are rapidly evolving, with many jurisdictions adopting stringent rules regarding documentation, traceability, and early-stage inspection. Standards such as ASME, API, ISO 27914, carbon dioxide capture, transportation and geological storage, and DNVRP guidelines emphasize the importance of a fully documented baseline to ensure that long-term geological storage and transport systems meet safety expectations. Regulators require operators to demonstrate that all reasonable measures were taken to identify pre-operation defects and that the facility was constructed within acceptable tolerances. Baseline inspections provide the evidence required to satisfy these expectations by proving compliance with welding qualifications, pressure test results, material certifications, and NDT documentation. In addition, regulators often expect operators to implement a continuous monitoring plan, and this plan relies heavily on accurate initial condition data to establish the expected operational envelope. In CCUS settings, specific attention is placed on injection wells, where baseline logs, cement bond evaluations, and pressure tests form legally required documentation. Failure to produce a valid baseline dataset can complicate compliance audits or lead to regulatory penalties and operational delays. Thus, baseline inspection aligns engineering practice with legal obligations, enhancing operational credibility and demonstrating responsible stewardship of injected CO2. Understanding CO2-driven degradation and the importance of baseline data. Material integrity in CCUS facilities is influenced by unique degradation mechanisms driven by CO2 and its impurities. Carbon steel in the presence of water and CO2 forms carbonic acid, which accelerates internal corrosion. Trace components like H2S or SOx can form highly corrosive environments, while oxygen can destabilize protective films, and water dropout increases localized pitting. In injection wells, temperature and pressure variations may cause stress corrosion cracking or thermal fatigue. Baseline inspections provide the clean starting point necessary to detect these degradation patterns early. They involve measuring initial wall thickness, documenting weld regions, verifying corrosion-resistant alloys, and capturing the original condition of coatings and linings. The baseline dataset establishes whether observed degradation during operations is new or linked to construction defects. This is particularly critical for CCUS operations because small anomalies can rapidly escalate in CO2 environments, especially in dense phase transport where flow velocities and phase transitions can amplify erosion corrosion. Proper baseline inspections also ensure material traceability so operators can verify that installed materials match design specifications for corrosion resistance. By building this foundational understanding, engineers can design mitigation strategies, optimize corrosion monitoring locations, and increase the reliability of future integrity assessments. Differentiating pre-operation and operational monitoring. Baseline inspection is fundamentally different from in-service inspection. While baseline inspection aims to document the original physical state of the asset, in-service inspections are periodic assessments designed to track changes over time. Without a baseline, operators lack the reference required to calculate corrosion rates, detect accelerated deterioration, or determine whether anomalies represent a true threat or a pre-existing condition. A baseline dataset typically includes ultrasonic thickness measurements, radiography, visual inspection documentation, and photographic records, all of which help establish the initial structural condition. In contrast, in-service inspections rely on trend analysis, comparing new data against baseline values to determine deterioration levels. For CCUS systems, this comparison is crucial because dense-phase CO2 operations can conceal damage until it becomes severe. For example, small internal corrosion pits might be undetectable without reference to baseline readings. Additionally, baseline inspection helps calibrate digital twins and integrity monitoring software, ensuring accurate predictive modeling for CO2 flow, temperature distribution, and corrosion progression. The reliability of future integrity decisions therefore depends heavily on the completeness and accuracy of the baseline inspection. Operational, safety, and financial risks. The absence of a proper baseline inspection introduces significant operational and financial risks. Without baseline data, operators must rely on assumptions about material conditions, weld integrity, and coating performance. This uncertainty can lead to incorrect risk assessments, which in turn may result in inappropriate inspection intervals or ineffective mitigation measures. In CCUS facilities, failure to detect early anomalies can result in accelerated corrosion, leakage, loss of containment, or injection well integrity failures. Such events not only pose safety hazards but can compromise environmental compliance and the legitimacy of CO2 sequestration claims. Financially, operators may face unplanned shutdowns, expensive repairs, regulatory penalties, or even legal liabilities. Insurance providers may also require baseline documentation to validate asset condition before offering coverage or determining premiums. Missing this critical step diminishes traceability, complicates root cause investigations, and weakens the operator's ability to demonstrate due diligence. Over the long term, poor baseline documentation leads to inefficient operations, increased uncertainty in predictive models, and reduced confidence among stakeholders, investors, and regulators. Therefore, conducting a robust baseline inspection is a proactive strategy that protects both operational reliability and corporate reputation. Applying baseline inspection to capture, transport, and injection systems. Baseline inspection requirements vary depending on the segment of the CCUS chain. In CO2 capture plants, inspections focus on absorber vessels, heat exchangers, amine systems, and ducting, ensuring that corrosion-prone areas are well characterized. For CO2 compression systems, vibration-sensitive components, rotating machinery alignment, and discharge piping integrity are scrutinized. Transport pipelines require comprehensive NDT and coating condition assessments, as these long-distance assets face internal corrosion, external corrosion, and potential mechanical damage. Baseline pig runs may be performed to record geometric imperfections. Injection wells require the most detailed baseline inspections, including cement bond logs, casing integrity tests, pressure integrity tests, and wellhead component verification. Operators must verify that the well barrier system is fully functional and that all materials are compatible with CO2, especially if impurities are present. Geological storage reservoirs also require baseline seismic and geophysical evaluations to monitor subsurface behavior. These baseline inputs collectively form the basis for long-term monitoring programs, ensuring that CCUS injection and storage operations remain stable, predictable, and environmentally compliant. A thorough baseline inspection across all system segments enhances integration between capture, transport, and injection operations, preventing unexpected failures across the CCUS value chain. Leveraging baseline data for digital twins, RBI, and predictive analytics. Baseline inspection data forms the foundation of digital integrity systems such as digital twins, integrity databases, and risk-based inspection, RBI, software. By integrating baseline information into these platforms, operators can simulate degradation pathways, forecast corrosion rates, and evaluate the impacts of operational changes on asset health. Digital twins rely on accurate initial geometric and material datasets to replicate asset behavior under various CO2 flow, temperature, and pressure conditions. Without accurate baseline inputs, predictive modeling results become less reliable, making risk management decisions more uncertain. Baseline datasets also enhance anomaly detection algorithms by providing reference points for ultrasonic measurements, vibration signatures, or temperature patterns. In CCUS applications, where long-term performance is critical to demonstrating permanent CO2 storage, digital monitoring systems must be highly accurate. Baseline inspection supports this accuracy, enabling operators to transition from reactive to proactive maintenance strategies. Over time, integrating baseline information into RBI programs helps optimize inspection frequencies, reduce costs, and improve safety margins. This holistic approach strengthens the integrity management program by combining real-world data, digital modeling, and engineering judgment.